Welcome back, design junkies. Supreme excellence consists in breaking the enemy's resistance without fighting Sun Tzu. The best designs don't fight the laws of physics. They make the laws of physics work for them.
Absolutely.
And today, we are staring down the barrel of a reality that feels pulled straight from, the most paranoid fringe dystopias you can even imagine.
It really does.
But I assure you, it is happening right outside your front door. I am talking about the modern surveillance state.
Right.
Because it is not just, a guy in a rusted-out van with a pair of binoculars and a lukewarm coffee anymore. We are looking at a literal, global panopticon.
That's entirely accurate.
Look at the level of security integration currently happening in places like the EU. Look at the aggressive, relentless push for a global exchange on digital IDs.
Yeah, the data sharing is unprecedented.
Exactly. We are talking about interconnected, cross-border databases that talk to each other in milliseconds.
It's a massive web.
And we're at a point where the sheer suffocating overreach of these automated systems. You could receive a speeding ticket in the mail because a camera system flagged a vehicle registered in your name, driven by someone else, while you were sitting in a completely different state.
That is the reality of automated enforcement, yeah.
It's insane. The limits to your constitutional freedoms are being tested right now by sensors, databases, and algorithms that do not sleep, do not blink, and do not care about your excuses.
They don't. They just process the data.
And with that, we are here to arm you with the ultimate weapon of defense, the weapon of engineering.
I like the sound of that.
So buckle up, Buttercup. As we speed past one of the most illuminating topics when it comes to your privacy, we are going to discuss the science, the creation, and the testing of products and materials you can use to arm yourself.
Okay, before we go completely down the rabbit hole here, I think it's really important we ground this conversation just a bit.
Sure, fair enough. Ground us.
Because when people hear about global databases and digital IDs and mass tracking, the temperature in the room instantly goes up.
Oh, for sure. People freak out.
Right. People get incredibly political about this stuff, and understandably so. But honestly, a thermal camera does not care who you voted for.
That's a great point.
The physics of how a silicon sensor captures light is completely agnostic. Whether you lean left, right, or consider yourself entirely off the political spectrum, the technological infrastructure making this mass tracking possible is an objective, undeniable reality.
It's just a machine doing its job.
Exactly. So our goal for this deep dive today isn't to debate the ethics or take a political side on whether these systems, whether they should exist.
Right. We're not policymakers.
We are simply looking at the raw, unfeeling capabilities of the systems described in our source material. We're looking at the math, the optics, and the physical parameters of how these machines observe the physical world.
And I think that's the perfect framing. Because panic doesn't actually help anyone.
It usually makes things worse.
If the limits of your freedoms are being tested by an invisible grid of sensors, your best defense is not, putting on a tinfoil hat and hiding in the woods.
Definitely don't do that.
It's having a...
Exactly. What we call visible light is just radiation with wavelengths roughly between 400 and 700 nanometers.
Which is nothing compared to the whole spectrum.
It's virtually nothing. But the surveillance grid doesn't care about our biological limitations. To a machine, our darkness is perfectly illuminated.
That is so creepy to think about.
It is. When we talk about night vision specifically, the Generation 3rd and Generation 3rd devices that define modern security, we are moving out of that visible band entirely.
Where are we going then?
We're moving into the near-infrared, or NIR band. This is roughly 0.7 to 1.4 micrometers.
Okay, let's break down exactly how those Generation 3rd tubes work, because I feel like they're basically magic to most people.
They do seem like magic.
Right. You put on these goggles, the world turns green, and suddenly you can see in the dark.
Yeah.
But what is physically happening inside that tube?
Well, it relies heavily on the photoelectric effect.
Okay, give us the physics 101 on that.
These systems use something called an image intensifier tube, and they are designed to gather whatever scarce ambient light is available in the environment.
Like just whatever light is floating around.
Yeah, starlight, moonlight, or even the diffuse glow from a distant city miles away. It gathers those incredibly rare photons into a component called a photocathode.
A photocathode, okay.
In Gen 3rd devices, this photocathode is typically made of gallium arsenide.
Gallium arsenide, got it.
When a photon hits this material, it transfers its energy to an electron, and if it has enough energy, it knocks that electron entirely out of the atomic structure and into the vacuum of the tube.
Wait, so we're translating light into electricity basically one photon at a time?
Exactly. It's a physical conversion. But one electron isn't going to give you a bright image.
Right, that would be pretty dim.
So a high-voltage electrical field aggressively accelerates that single ejected electron toward a second component, which is called the microchannel plate.
The microchannel plate, what does that look like?
Think of this as a microscopic honeycomb made of millions of tiny glass tubes.
The millions of them.
Yeah. When that primary electron flies into one of these tubes, it violently strikes the wall, and that knocks loose several more electrons.
Oh, like a chain reaction.
Exactly.
Right.
Those secondary electrons bounce down the tube, knocking loose even more. It's a cascading avalanche.
That's wild.
So one photon goes in, and thousands of electrons come flying out the other side.
Okay, but then what? How do those electrons turn back into a picture I can actually look at?
Those multiplied electrons are then slammed into a phosphor screen at the back of the tube.
Ah, phosphor. Like old TVs.
Precisely like old TVs. The kinetic energy of the electrons excites the phosphor, causing it to emit photons of visible light.
And it's usually green, right?
Almost always green, because the human eye is highly sensitive to variations in green shades. It gives you the best detail.
That makes sense.
So you've taken a dark near-infrared scene, converted it to an electrical signal, amplified it exponentially, and printed it on a tiny green television screen for your eye.
That is just incredible engineering.
But there is a catch. If there is absolutely no ambient light, say you are in a pitch-black basement with no windows, these systems use active IR illuminators.
Active illuminators, what does that mean?
They fire invisible near-infrared LEDs, like a flashlight, that only the goggles can see.
Okay, I always like to explain traditional night vision to people by comparing it to a hearing aid, but for light.
That's actually a really good analogy.
Right, because a hearing aid works wonderfully, but it only works if there is a tiny little bit of noise in the room to amplify.
Right. It needs something to work with.
If you're sitting in a total vacuum, you can crank the volume on a hearing aid all the way to maximum, and it does absolutely nothing.
It's just silent.
Night vision is exactly the same. It needs a few stray photons to bounce around.
Completely dependent on them.
So if you are in heavy fog, thick smoke, or deep in a subterranean cave with zero ambient light, and you don't want to give away your position by turning on your active IR flashlight,
then you're out of luck.
exactly. That $10,000 Gen III scope basically goes deaf. It is totally blind.
And that exact vulnerability, the reliance on ambient light or active illumination, is why the surveillance industry relies so heavily on what is arguably the true privacy killer.
And that is
Thermal vision.
thermal.
Thermal operates in the long-wave infrared band, or LWIR. We are talking about wavelengths spanning from 8 to 15 micrometers.
Okay, so a much longer wavelength than night vision.
Yes, and thermal imaging doesn't care if there is ambient light. It does not need a single photon of starlight to function. It is a completely passive system.
Because it's not looking for light bouncing off objects, right? It's looking for the energy the object is actively creating itself.
Exactly. It detects the literal heat emitted by anything in the universe that is above absolute zero.
Which is everything.
Pretty much. Every living biological thing, every running engine, every piece of electronics, even the friction of a car tire rolling across asphalt.
Wow.
We are all constantly radiating energy in the LWIR band. And inside a thermal camera, you won't find a standard silicon CMOS sensor like the one in your smartphone.
What's in there instead?
You find an array of microscopic components called microbolometers.
Microbolometers. Okay, let's unpack the microbolometer because I feel like this is where the physics get really wild.
It is a beautiful piece of technology.
How does a microbolometer actually translate my body heat into an image?
A microbolometer is essentially a microscopic resistor. Usually they're made of vanadium oxide or amorphous silicon.
Okay.
And they are tiny. We are talking individual pixels that are maybe 12 to 17 microns wide.
That's incredibly small.
When long-wave infrared radiation heat basically strikes the material of the microbolometer, the material physically absorbs that energy and its temperature rises slightly.
So the pixel itself actually gets hot.
Yes, very slightly. And as its temperature rises, its electrical resistance changes.
Ah, got it.
The camera's processor runs a current through the array, measures the exact resistance change of every single microscopic pixel, and uses that data to calculate the exact temperature of whatever you are looking at.
And that's how it builds the picture.
Right. It then assigns a color to that temperature to build the image you see on the screen.
Okay, so this brings up the immediate question everyone asks when they realize cameras can see literal body heat.
I can guess what you're going to ask.
If these things are just measuring raw thermal radiation, can they see me through the walls of my house?
Right.
Or like if I'm driving down the highway at night, could a thermal camera mounted on an overpass see
Well,
my glowing body heat through the closed windows of my car?
that is the natural fear, yes.
Hmm.
But it entirely misunderstands the physical properties of how electromagnetic radiation interacts with different
Okay,
materials.
so what's the answer?
The short answer is no. They cannot see through walls or glass.
Oh, thank goodness.
Thick, dense materials like brick, wood, and drywall completely block and absorb long-wave infrared radiation. But the glass aspect is the truly fascinating part.
Yeah, explain this, because to our eyes, glass is completely transparent. It lets visible light right through. Why does it stop a thermal camera?
It comes down to the atomic lattice structure of the glass itself. Standard glass. The silica glass used in your car windows in your house is completely opaque to long-wave infrared.
Opaque, like a brick.
Exactly like a brick. The silicon-oxygen bonds within the glass happen to resonate at the exact frequencies of long-wave infrared light.
Oh, wow.
So when your body heat hits the window, the glass absorbs that energy and blocks it from passing through.
That's so counterintuitive.
It is. To a thermal camera, a closed glass window doesn't look like a window at all. It looks like a solid glowing wall reflecting the ambient heat of the environment.
So I could be standing right behind a big pane of glass.
You can stand right behind a sheet of glass, completely visible to the naked eye, and a thermal camera will not see you at all.
Which means the people building these surveillance cameras have a massive engineering headache, don't they?
Oh, absolutely.
Because they can't just slap a piece of standard glass over the front of their incredibly expensive micropolometer sensor to protect it.
No, they can't.
Because the glass would literally blind their own sensor.
Precisely. This is a massive manufacturing hurdle for the military and surveillance contractors. They have to use highly specialized materials for their thermal lenses.
What do they use instead of glass?
They rely heavily on elements like germanium or advanced chalcogenide glasses.
Wait, chalcogenide glass. I know what silica is, but what makes a chalcogenide different?
Chalcogenide glasses are made from chalcogen elements. These are elements in group 16 of the periodic table, specifically sulfur, selenium, and tellurium.
Okay, chemistry class flashback.
Right. When you form a glass out of these elements, their atomic bonds are much weaker and heavier than the tight silicon-oxygen bonds in standard glass.
And why does that matter?
Because the bonds are heavier and weaker, they vibrate at much lower frequencies. This means they do not resonate with or absorb long-wave infrared radiation.
Ah, so the heat passes through.
The thermal energy passes right through the lattice. But these materials are incredibly expensive, highly specialized, and ironically, while they transmit IR energy beautifully, many of them are completely opaque and look entirely black to the human eye.
That is wild. The lens of the thermal camera looks black to us, but is crystal clear to the machine.
Exactly. It's an inverted reality.
But wait, if we know how these passive systems watch the environment, we have to talk about what happens when the panopticon stops just passively watching.
I guess it doesn't just watch anymore.
Right. Modern surveillance isn't just a camera sitting back and watching heat signatures drift by on a screen. It is actively throwing invisible nets out into the physical world to measure the exact three-dimensional topography of your face.
We are transitioning from passive observation into the realm of active mapping now.
Which is terrifying.
This is primarily achieved through technologies like structured light and time-of-flight sensors. To map 3D space, a surveillance system won't just take a flat picture of you.
What does it do?
It'll use an IR projector to blast an incredibly dense grid of light onto a moving target, sometimes up to 30,000 microscopic near-infrared dots.
30,000 dots on a human face.
Easily. The system projects the dots, and a secondary infrared camera observes that grid.
Okay, so it's looking at the dots on my face.
Yes. By carefully measuring how those thousands of dots physically deform as they drape over the complex contours of your cheekbones, the bridge of your nose, the curve of your jawline.
It builds a map.
Exactly. The system calculates depth. Alternatively, in a time-of-flight system, it measures the literal picoseconds it takes for those photons to bounce off your face and return to the sensor.
Picoseconds. That's absurdly fast.
By combining these techniques, the system builds a highly accurate topographical 3D mathematical mesh of your exact identity.
So it isn't looking at a picture of you.
Not at all. It is analyzing a topographical sculpture of you.
But I mean, the real world is messy.
Very messy.
I get how that works if I'm unlocking my phone in my living room.
Yeah.
But out on the street, You've got smog, you've got pouring rain, you've got heavy thermal turbulence radiating off hot asphalt in the middle of summer.
Environmental noise is a huge factor.
How do these delicate little microscopic laser grids survive traveling 30 yards through all that atmospheric garbage to hit my face?
That is the core engineering challenge, and they solve it through highly advanced geometry.
Geometry.
Engineers realized decades ago that if you just project a simple, standard laser grid, it gets completely scattered and destroyed by what optical physicists call dirty air.
Dirty air. So smog, rain, thermal layers.
Exactly. To counter this, they don't project a simple grid. They utilize fractal structured light beams.
Okay, fractals. Like the trippy mathematical patterns that zoom in forever.
That's the one.
How does a camera project a fractal?
They use specialized optical diffusers to shape the laser light into self-similar mathematical geometries. A common one is based on the Vicsek fractal.
The Vicsek fractal.
The defining characteristic of a fractal is self-similarity. The pattern looks the same whether you zoom in on a microscopic piece of it or look at the whole thing.
Right, I've seen animations of that.
Because these specific light fields possess that structural self-similarity, they have an incredible ability to resist atmospheric interference.
I'm sorry, how does math stop smog?
It doesn't stop the smog, it survives it. As the fractal beam propagates through heavy turbulence, parts of the beam will inevitably scatter or phase shift.
So some of the light gets messed up.
Yes, but because the underlying structure is entirely self-similar, the beam maintains its core informational integrity.
Doesn't lose the shape.
Right. As it travels, the undisturbed parts of the fractal effectively interfere with the scattered parts, allowing the overall pattern to, quote-unquote, self-heal over distance.
That is mind-blowing. Self-healing light.
It ensures that the intricate mathematical pattern remains intact enough to map the microcontours of your face from a significant distance, even through a downpour.
It's like the camera is trying to project a highly complex QR code onto your face from across a smoky room and then read it back.
That's a great way to visualize it.
So if I'm an engineer trying to build a countermeasure, trying to turn off the camera is useless. It's way out of my reach.
You can't touch the camera.
My goal has to be to smear the ink of that QR code before the camera can read it off my face. So how do we mechanically scramble a fractal beam?
The ultimate weapon against structured light is chaos.
Chaos.
If the surveillance system relies entirely on perfect fractal self-similarity to calculate depth, your objective is to introduce catastrophic phase interference at the point of contact.
Okay, how do I do that?
You can achieve this by engineering materials with diffraction gratings, microlens arrays, or highly scattering volumetric diffusers.
Let's explain diffraction gratings because they seem crucial here. What is physically happening when the laser hits one?
A diffraction grating is an optical component with a microscopic periodic structure. Think of thousands of incredibly tiny parallel ridges etched into a surface.
Like the grooves on a vinyl record, but way smaller.
Exactly. When the pristine, self-healing fractal beam hits those ridges, the light is forcibly split and diffracted into multiple overlapping paths.
So it bounces all over the place.
Instead of reflecting cleanly, the light waves are forced to crash into one another. This creates massive destructive interference.
You're breaking the fractal.
Precisely. The self-similarity breaks down entirely. The precise spatial phase of the light is ruined.
Wow.
So when the camera looks back at your face, the perfect 3D topographical mesh the AI was expecting to calculate is instantly reduced to unrecognizable, randomized static.
The system can't map a face if the measuring cape itself has been shredded into a million pieces.
That is exactly the physics of the countermeasure.
Which brings us to a massive pivot point in this arms race. Because let's say I'm in a scenario where I cannot physically block or scramble the structured light.
Okay.
Or what if the system is just using an incredibly high-resolution visible light camera, just a regular 4K camera?
It happens all the time.
If I can't scramble the physics of the photons, I have to move up the software chain. I have to scramble the brain that is analyzing those photons.
You have to target the AI directly.
We are moving from the physics of light straight into the cognition of deep neural networks.
We are entering the realm of adversarial patch attacks.
I love this topic.
It's fascinating. Modern surveillance does not rely on a human sitting in a control room looking at a wall of monitors anymore.
Too much footage.
Way too much. It relies heavily on convolutional neural networks, or CNNs, to process, classify, and track everything in a video feed autonomously.
I hear the term CNN constantly in AI circles. Give me the baseline on how a convolutional neural network actually decides it is looking at a human being.
Well, a CNN doesn't see the way we do. It applies a series of mathematical filters called convolutions across an image.
What are the filters looking for?
The first layers of the network look for very basic features: sharp edges, gradients, contrasting colors.
Simple lines.
Yes. As the data passes deeper into the network, it starts combining those edges into shapes and eventually into highly complex geometric and textural patterns that it has been trained to recognize as, say, a human shoulder or a human face.
And a patch attack.
A patch attack exploits the exact mathematical weights the network assigns to those specific features.
So unlike digital noise, where a hacker corrupts the JPEG file inside the computer, a patch attack happens out in the physical world.
Exactly. These are physical printed stickers, wearable patterns, or clothing designs, and they are generated using adversarial training.
Adversarial training, what's that process like?
Engineers use gradient descent algorithms to essentially reverse engineer the CNN. They ask the computer, what exact arrangement of pixels will maximally activate the stop sign category while simultaneously minimizing the human category?
So they're forcing the AI to see something else.
The result is a localized, highly visible modification that acts as a cognitive override to the AI.
It's essentially a visual exploit.
Right.
Like a hack, but printed on paper.
Yes. When the CNN scans the image, it hits the adversarial patch. The mathematical weight of the pattern is so overwhelmingly strong and so specifically tuned to exploit the network's vulnerabilities that the AI gets completely confused.
What happens when it gets confused?
It might suddenly classify the person wearing the patch as a potted plant or a toaster, or it might just fail to see an object at all.
It's just total invisibility.
Similar to how researchers have famously hidden physical stop signs from autonomous vehicles by applying just a few carefully calculated black and white stickers to the metal, the AI looks right at the stop sign and sees nothing.
But this is always where I get stuck on adversarial patches.
The human element.
Yeah. If I'm walking down the street or walking through an airport wearing a crazy psychedelic static noise sticker plastered across my chest to fool the ceiling cameras,
Right.
isn't an actual human security guard going to spot me instantly?
Hmm.
It feels like you are trading invisibility to the machines for massive, glaring visibility to any human with a pulse.
That is definitely the most common critique of adversarial patches, but it fundamentally misunderstands the modern security landscape.
How so?
First, patch attacks are specifically engineered for a reality where human oversight is increasingly minimal. These systems process thousands of hours of footage autonomously.
Oh, so nobody is actually watching the screen.
A human only looks at the screen if the AI flags an anomaly. If the AI doesn't see you, the human never gets the alert.
But what if a guard just happens to be looking out the window?
That brings us to the second, much more advanced point. The attackers and the privacy engineers are getting much smarter. They are no longer using chaotic, psychedelic static that screams for attention.
What are they using?
They are designing adversarial patches to look like completely natural objects in the environment. This is called content-based camouflage.
How do you hide adversarial math in plain sight? That sounds impossible.
By constraining the adversarial algorithm during the generation phase. You force the algorithm to weave the mathematical exploit into the shape of a corporate logo, a piece of street graffiti, or a standard graphic t-shirt.
Okay, give me an example.
The algorithm subtly shifts the colors and edges within the boundaries of a picture of a flower, for instance.
So it just looks like a flower.
To a human guard glancing at you, you are just wearing a shirt with a slightly abstract floral design. It arouses zero human suspicion. But to the CNN analyzing the pixel weights, that flower is screaming incredibly complex, destabilizing data that completely devastates the detection algorithm.
The arms race here is moving so fast it's terrifying. I mean, according to the research sources we are diving into, there are some incredibly wild evasion tactics currently being deployed in the wild.
The field is accelerating.
You're talking about dynamic adversarial patches. These aren't just printed on a cotton shirt. They are displayed on flexible, wearable, flat screens.
Yes.
The screens are linked to sensors that detect the position and angle of the camera tracking them, and they literally morph and change their adversarial pattern in real time to maintain the perfect angle of attack against the AI.
Yes, the complexity is escalating rapidly, and the sources also detail a fascinating system called T-patch, which introduces a multimodal element to the attack.
T-patch. I read about this.
T-patch is an adversarial pattern that is acoustically triggered.
Wait, acoustically triggered? Like sound. How does sound affect a camera?
It exploits the hardware vulnerabilities of the camera itself. Most modern security cameras have built-in microphones, and many use CMOS sensors with rolling shutters.
Okay, so the camera has a mic and a specific way of capturing video.
The T-patch system remains completely benign and undetectable to the AI under normal circumstances. But when a specific, often high-frequency, inaudible sound wave hits the camera,
Oh, I see where this is going.
it physically vibrates the internal components. This acoustic injection can induce slight piezoelectric effects or interfere with the timing of the rolling shutter just enough that it slightly blurs or alters the way the camera captures the visual field.
So you hit the camera with a sound wave, and the physical vibration causes the camera to capture the image of the patch slightly differently.
Exactly. The acoustic vibration changes the physical capture just enough that the previously benign patch suddenly perfectly aligns with the adversarial weights.
And instantly hides the target.
It is a brilliant cross-domain attack. We're also seeing physical materials-based attacks like the LMBC, which stands for leaf-like mask barcode.
Let's talk about the LMBC, because this combines the AI scrambling with thermal evasion, right?
Yes, because beating an AI with a printed patch only works in visible light.
Right. Thermal wouldn't care about a printed flower.
The LNBC is designed to create adversarial patches in the thermal spectrum. It uses incredibly cheap, readily available materials, specifically thin aluminum sheets and craft paper.
Why aluminum and paper?
It goes back to emissivity, which we will discuss deeply in a moment. Aluminum has incredibly low thermal emissivity, meaning it traps heat and looks cold or black to a thermal camera. Craft paper has high emissivity, meaning it radiates heat well.
Ah, contrast.
By cutting these materials into specific leaf-inspired contour masks and layering them, engineers can create high-resolution, camera-visible adversarial patches that show up brilliantly on a thermal imager.
So the AI looking at the thermal feed gets confused too.
It gets completely confused by the geometric shapes of the hot and cold spots, allowing for multi-angle evasion without needing any electronic components at all.
It is literal engineering warfare. And the researchers in the source material, they don't just build this stuff and guess if it works.
No, they're rigorous.
They outline a 5-stage evaluation ladder for anyone trying to build surveillance defense.
It's a critical framework for testing. Stage 1 is digital tests. You take a photo, overlay the patch digitally on a computer, and see if it fools the AI on a per-frame basis.
Sounds easy enough.
It is the easiest test to pass. Stage 2 moves to lab physical tests. You print the patch, put it on a mannequin in a controlled room with perfect lighting, and see if the physical print works.
Okay, stepping it up.
Stage 3 introduces distance and camera variation. Does it work from 10 feet, 50 feet? Does it work on a cheap webcam and a high-end security camera?
But stage 4 is where most of these DIY hacks fall apart completely, right?
Yeah.
Temporal persistence.
Yes. Stage 4 tests against multi-object trackers. Modern systems don't just evaluate single frames in isolation. They maintain an identity file over time. They track your trajectory.
Like your speed and direction.
If your patch fools the camera for a split second, but the AI remembers your speed and vector from the previous frame, it will just interpolate your position and maintain the lock.
It just guesses where you are.
To pass stage 4, your countermeasure must be robust enough to break the tracking algorithm continuously, frame after frame, across multiple angles.
And finally, stage 5. Multimodal risk. Can you beat the visible light cameras and the thermal sensors simultaneously?
That is the peak.
Which brings us to the most monumental hurdle in this entire engineering challenge. Because tricking a neural network with a cleverly designed floral shirt is amazing if you're only dealing with a visible light camera.
True.
But how do you disappear when your very biology, you're pumping blood and your body heat is radiating out into the environment, betraying your location to any passing thermal imager?
It's the hardest problem to solve.
We have to dive deep into the thermodynamics of emissivity.
Emissivity is the central physics problem of thermal camouflage. It is a measure of how efficiently a material radiates its internal thermal energy out into the surrounding environment.
How does the scale work?
The scale goes from 0, which is a perfect thermal mirror that radiates nothing, to 1, which is a theoretical black body that radiates energy perfectly.
And unfortunately for anyone trying to hide, human biology is basically designed to dump heat. Human skin sits at a massive 0.98 on the emissivity scale.
We are essentially walking space heaters.
Agree.
We radiate heat incredibly efficiently in the long-wave infrared band. So to a thermal camera, a human being is a glowing beacon against the cooler background of the environment.
So the obvious question, And I will fully admit I have tried this in my own backyard with a cheap FLIR camera attached to my phone.
I think everyone has thought about this at least once.
Why can't I just go to a camping store, buy a $5 aluminum foil space blanket, wrap myself up like a burrito, and call it a day? Aluminum reflects IR, right? So shouldn't I be invisible?
You should tell the audience what happened when you tried it.
I looked like a giant glowing baked potato.
Exactly.
Like for the first 30 seconds, I was totally invisible. The camera just saw the cold reflection of the sky. But a minute later, the blanket started glowing white hot on the screen. It was actually worse than just standing there in a t-shirt. Why did that happen?
It happened because you forgot to account for conductive heat transfer.
Conductive heat transfer.
If we look at the laws of thermodynamics, we see exactly why the space blanket fails miserably as camouflage. Mylar and aluminum are fantastic at reflecting infrared radiation, yes. They have very low emissivity.
Right.
But if that thin mylar is physically touching your skin or even resting tightly against your clothing, your body heat doesn't radiate, it conducts.
It transfers directly into the metal.
Exactly. Because the metallic film is so incredibly thin, it has very little thermal mass, it heats up incredibly fast.
Oh, so I'm just heating up the blanket.
Within minutes, the blanket itself absorbs your body heat and reaches your core temperature. And because the blanket has a much larger, flatter surface area than your body, it actually makes you a larger, more distinct target.
That explains the glowing potato effect.
It begins to glow brilliantly on the thermal camera. To defeat thermal imaging, you don't just need a reflective material, you need thermal decoupling.
Thermal decoupling, meaning I have to stop the heat from ever reaching the metal in the first place.
Yes. You have to isolate the heat source, your body, from the low emissivity outer layer. You need an incredibly efficient insulating layer in between.
Okay, so we need inspiration on how to build this. And usually, the most ruthlessly efficient engineer on the planet is Mother Nature.
Nature has solved this.
The sources bring up an incredible biological example: the Saharan silver ant. This little insect survives in one of the most brutal, scorching thermal environments on Earth.
It's an amazing creature.
And it does it without sweating or relying on internal cooling mechanisms. It does it through pure structural biomimicry.
The Saharan silver ant is an absolute marvel of thermal management. It survives midday in the desert by using dense arrays of microscopic, triangularly shaped hairs that cover its entire body.
Triangular hairs.
Yes. These hairs are engineered by millions of years of evolution to induce a very specific optical phenomenon called Mie scattering, combined with total internal reflection.
Break down Mie scattering for me. What is happening when sunlight hits those triangular hairs?
Mie scattering occurs when light hits particles or structures that are roughly the same size as the wavelength of the light itself.
Okay.
The triangular geometry of the ant's hairs perfectly corresponds to the wavelengths of solar radiation. What this means in practical terms is that the hairs act as a highly reflective mirror to the near-infrared and visible radiation bombarding the ant from the sun.
So the light bounces off the hairs instead of being absorbed.
Exactly.
So it acts as a sun shield. But how does it get rid of the ant's own body heat?
That is the genius of the triangular shape. While it reflects the sun's incoming near-infrared light, the geometry simultaneously maximizes the emissivity of heat in the mid-infrared spectrum.
Wait, it does both.
Yes, it acts like a thermal exhaust pipe, efficiently dumping the ant's internal body heat out into the cold sink of the open sky.
That is brilliant.
The ant is minimizing its energy absorption while simultaneously maximizing its heat rejection.
And the craziest part is that material scientists aren't just studying this, they are actively replicating it in the lab.
They
are synthesizing bionic structures using zinc oxide or ZNO microcrystal bars, and they are coating them onto flexible polyester fabrics. They're literally printing fake microscopic ant hair onto shirts to block thermal radiation.
It's cutting-edge biomimicry.
But as cool as ant hair shirts are, there is another material detailed in our stack of sources that feels like absolute black magic. It is the holy grail of privacy tech.
Aha!
Enzenes.
Specifically, a compound called Ti3C2 takes.
Enzenes are a relatively new, incredibly exciting family of two-dimensional inorganic compounds. They were only discovered in 2011.
It's very recent.
They consist of layers of transition metal carbides, nitrides, or carbonitrides that are only a few atoms thick. They possess a combination of electrical and optical properties that engineers have been chasing for decades.
What makes them so special for camouflage?
The holy grail of thermal camouflage is a material that is visible black, but IR white.
Visible black, but IR white.
Okay. You want something that completely blends into the dark to the human eye, but acts like a mirror to a thermal camera. Emzenes achieve this beautifully.
How does the chemistry work?
The Ti3C2 part of the formula refers to the titanium and carbon lattice, which has incredibly high electron mobility. This makes it highly conductive, like a metal.
Okay, so it conducts electricity.
And because it is highly conductive, it reflects long-wave infrared radiation perfectly. It has incredibly low emissivity.
So to a thermal camera, it looks white or reflective,
Yeah.
radiating almost no thermal energy. It just reflects the cool background of the room.
Yes, but the TX in the formula refers to surface terminations, oxygen, hydroxyl, or fluorine atoms attached to the surface of the 2D layers.
And what do those do?
These surface terminations drastically alter how the material interacts with visible light. They cause the material to absorb almost all photons in the visible spectrum.
So to the naked human eye, a sheet of this Emzene material appears completely flatly black.
Exactly.
The sources show an incredible practical demonstration of this using anti-counterfeiting ink. The researchers took this Emzene solution and used it to write the acronym HKUS on a membrane.
A great experiment.
For the letters HK, they used standard run-of-the-mill black paint. For letters UST, they used the liquid Emzene solution. If you or I look at it with our human eyes, it just looks like a solid black word painted on a sheet. You cannot tell the difference between the letters.
But the second you look at that exact same piece of paper through an IR thermal imager, the illusion breaks completely.
Because of the emissivity.
Right. The standard black paint of HK has high emissivity, so it blends perfectly into the background heat of the membrane and practically vanishes.
And the other letters.
The UST, written in Emzene, has incredibly low emissivity. It reflects the cold ambient temperature of the room. So on the thermal screen, the UST glows clearly as a distinct cold shape because of the massive contrast in thermal emissivity.
Do you realize what that means for adversarial patches?
It's a game changer.
You could literally paint a massive, complex adversarial patch on the front of a black t-shirt using Emzene ink. To a human security guard, you're just wearing a plain black t-shirt.
Exactly.
But to the thermal camera, your chest is screaming with geometric patterns that completely crash the AI's detection algorithms.
It is the ultimate content-based camouflage, and this exact manipulation of chemical properties ties directly into how advanced military laboratories approach thermal camouflage for vehicles.
Oh, like tanks and stuff.
Yeah, it isn't just about painting green and brown splotches on a tank and hoping it blends into the forest. Military chemists are actively altering the fundamental chemical bonds of the polymers within the paints themselves.
How do chemical bonds affect thermal cameras?
Every chemical bond vibrates at a specific frequency. Scientists know that carbon-hydrogen bonds, which are incredibly common in standard paints and plastics, inherently absorb and emit specific bands of infrared radiation that match the peak sensitivity of thermal cameras.
So the paint itself is glowing to the camera.
Yes. So military chemists formulate specialized coatings using chlorinated resins like polyvinyl chloride, purposefully eliminating those CH bonds and replacing them with carbon-chlorine bonds.
Which vibrate at a different frequency.
Exactly. A frequency outside the detection range of the camera. This drastically lowers the overall IR emission of the painted vehicle, significantly reducing its thermal signature, while still allowing the chemist to mix in the visible green and brown pigments to fool the human eye.
All right, so let's take stock. We have armored the body using thermal decoupling and Emzenes. We have manipulated our heat signatures. We are wearing adversarial patches to fry the AI.
We are well protected so far.
But there is a glaring, massive hole in our defense. What about the glass?
The glass problem again?
If I am wearing a full Emzene suit, I'm basically a blind ninja. I have to have eye holes. And if I'm driving a car, my windshield is a giant, transparent vulnerability. I can't paint my windshield black.
No, you cannot.
How do we protect our eyes? How do we shield our car windows? And better yet, how do we turn the camera's own light against it? We need to talk about advanced optics.
The heavy, fragile silica glass of the past is rapidly being replaced in the optics industry by highly specialized polymers. Materials like PMMA, which is acrylic, polycarbonate, and PEEK.
So plastics.
High-end polymers, yes. These polymers offer incredible impact resistance, which is great for safety, but more importantly, their chemical structure allows them to be precisely molded and embedded with nanostructures that manipulate light on a microscopic level.
And the research highlights a mind-blowing breakthrough from Fujifilm in this exact area.
It's a stellar piece of technology.
They developed a metamaterial film that you can apply directly to glass or polycarbonate. And this film is embedded with microscopic hexagonal silver nanodiscs. Let me give everyone an idea of the scale we are talking about here.
The scale is hard to comprehend.
These silver discs are 120 nanometers wide. A human hair is about 80,000 nanometers wide, and these discs are only 11 nanometers thick.
The scale is essential to their function, and what those tiny silver hexagons do is utilize a phenomenon called localized plasmon resonance, or LPR.
Explain LPR. What happens when light hits a nanodisc?
Metals like silver have a sea of free electrons on their surface. When light, which is an electromagnetic wave, hits those electrons, the electric field of the light causes the electron cloud to oscillate back and forth.
Okay, so the light makes the electrons vibrate.
If the size and shape of the silver particle are precisely tuned, that electron cloud will oscillate in perfect resonance with a specific wavelength of light. This is localized plasmon resonance.
And when they resonate?
When the electrons resonate, they strongly scatter and reflect that specific wavelength back outward.
So by making the discs exactly 120 nanometers wide, Fujifilm engineered them to resonate perfectly with near-infrared light.
Precisely. By perfectly tuning the geometry of these silver discs, engineers have created a film that flawlessly reflects near-infrared light, acting as an impenetrable heat barrier.
But what about visible light?
Because the discs are so small and spaced out, they do not resonate with the shorter wavelengths of visible light. Visible photons slip right past them. So the film remains entirely transparent to human vision and radio waves.
The applications for that are insane. You could put this film on your car window. Your GPS still works perfectly. Your cell phone gets a signal. You can see the road clearly at night. But to a police IR camera trying to scan your face, your windshield looks like a solid, impenetrable mirror.
This is the foundation of modern thin film optics, which allows us to create what are known in the industry as hot mirrors.
Hot mirrors.
Hot mirrors are designed to reflect heat IR while transmitting visible light. By carefully stacking dozens of alternating layers of dielectric materials with different refractive indices.
Or using transparent conducting oxides like indium tin oxide.
Right. We can engineer a piece of polycarbonate that creates constructive interference for visible photons, letting them pass right through, but creates massive destructive interference for infrared photons.
So the camera's active IR illuminator, your transparent glasses look like a solid brick wall.
Yes.
But we don't just want to build a wall and hide behind it. We want to fight back. If the surveillance state is shining a flashlight in our eyes, we want to blind them.
Offensive optics.
Let's talk about retroreflection. I want you to imagine you have a tennis ball, and you throw it at a standard brick wall. Usually the ball bounces off at a random angle and rolls away.
Right.
Retroreflection is like throwing that tennis ball at the wall and having it fire straight back down the exact same trajectory right back into your hand.
It relies on corner cube reflectors or specialized microprisms. When a beam of light enters these structures, it bounces off 3 internal, mutually perpendicular surfaces.
Like a mirror box.
The geometry ensures that no matter what angle the light entered from, it is reflected exactly 180 degrees back toward the source.
So if we embed these retroreflective microprisms into the frames of our glasses, or weave them into the collar of our jacket, we completely change the power dynamic.
It's an aggressive countermeasure.
When a facial recognition camera fires an active, highly concentrated near-infrared laser beam at you to map your face, those microprisms catch that invisible light.
And they don't scatter it.
Instead of scattering it, they bounce it straight back down the exact same path with such intense focused energy that it physically blows out the camera's sensor.
Yes, you completely exceed the camera's dynamic range.
You are essentially using the camera's own flashlight to blind it.
It is an incredibly elegant, purely mechanical solution. It requires no batteries on your end.
I love that.
However, to understand the true scope of what we are up against, we have to look past current lenses and look at the terrifying future of night vision technology itself.
It gets worse.
As we discussed earlier, historically, night vision required bulky vacuum tubes, heavy battery packs, high-voltage fields, and complex photocathodes. It was heavy tactical gear.
Stuff you'd see in a military movie.
But a recent breakthrough detailed in the sources involves a brand new ultra-thin coating made from a non-local metasurface of lithium niobate.
This is the part that genuinely gave me chills when I read it. We are talking about replacing a massive, heavy tactical helmet with a film that is as thin as plastic cling wrap. How on earth does lithium niobate replace a vacuum tube?
It completely throws out the photoelectric effect we discussed earlier.
So no electrons bouncing around.
None. Instead of converting photons to electrons, multiplying them, and converting them back to light, this lithium niobate metasurface uses a branch of physics called nonlinear optics. It relies on a process called some-frequency generation.
Okay.
The metasurface is etched with microscopic resonant structures. When an incoming invisible infrared photon, say, at a wavelength of 1550 nanometers hits the surface, it is temporarily trapped in the resonator.
Okay, photon trapped.
Simultaneously, the device shines a secondary, continuous laser beam called a pump beam across the surface. Through the nonlinear properties of the lithium niobate, the incoming infrared photon literally physically mixes and combines with a photon from the pump laser.
Wait, their energies add together?
Yes.
They just fuse?
Essentially, yes. They combine to instantly emit a brand new single photon with a much higher energy level and a much shorter wavelength. Specifically, around 550 nanometers, which is visible green light.
Whoa.
It is directly upconverting the infrared light straight into visible light right there on the surface of the film.
So there are no electrons.
Yep.
There are no vacuum tubes. You are directly altering the frequency of the light on a microscopic quantum scale.
The implications are profound. Because it doesn't require high-voltage vacuum tubes or heavy microchannel plates, the technology is essentially weightless and paper-thin.
Think about what that actually means for the surveillance grid. If night vision no longer requires a giant, expensive, highly visible tactical camera housing,
Right.
if it can be applied like cling wrap to a regular pair of reading glasses worn by an undercover officer, or coated onto a tiny hidden pinhole lens in a street lamp, or embedded into the glass of an office building window, the grid is about to become exponentially more invisible.
It will be everywhere and nowhere.
We aren't going to see the cameras that are watching us in the dark anymore. The panopticon will be utterly seamless.
Which is exactly why knowing the theoretical science of how these cameras work is only half the battle.
We need application.
If we are to survive this increasingly invisible grid, we must apply a core engineering principle to build a real-world solution. In the aerospace and manufacturing industries, when lives are on the line, we use a methodology called FMEA failure mode and effects analysis.
FMEA, I've heard of this in aviation.
Yes. You look at a highly complex system, you painstakingly identify every single way it could possibly fail, and you engineer redundant countermeasures for every single mode. We must apply FMEA to our personal privacy.
So no single points of failure.
You cannot rely on a single trick. If your adversarial patch gets wet and stops working, you need a backup. We have to layer the defense.
Okay, let's do it. Let's build a hypothetical, full-stack privacy loadout right now, using everything we've talked about. We are building the ultimate anti-surveillance suit.
Starting with the base layer, right against the skin. Our primary failure mode here is thermal conduction. We must achieve thermal decoupling.
We can't be baked potatoes.
Exactly. We cannot let our 0.98 emissivity body heat reach the outer layers. So we are using advanced aerogels, which are essentially solid smoke made of 99% air, offering incredible thermal insulation and closed-cell insulating foams. We trap the heat before it can conduct outward.
So I am thermally isolated. Now moving to the middle layer, we must address the broader electromagnetic spectrum.
Because it's not just heat.
Even if I block heat, my cell phone, my smartwatch, and my car key fob are emitting RF signals. We incorporate conductive shielding. We use metallized fabrics, nylons tightly woven with microscopic silver or copper threads to create a wearable Faraday cage.
That's a great layer.
This blocks stray electromagnetic signatures from leaking out and provides a secondary internal reflective layer to bounce any residual thermal energy back toward the body.
Then the outer layer, this is the visual and thermal camouflage layer. This is where we attack the AI.
Let's fry the CNN.
We deploy asymmetric IR reflective patterns. We are using the LMBC leaf masks we discussed earlier to break up the thermal geometry. Or better yet, we are printing highly complex, mathematically generated adversarial patches using that visible black IR white MS-Scene ink.
So to the human eye, it just looks like high-end streetwear.
To the machine, we are actively scrambling the structured light grids and breaking the recognizable human geometric forms that the convolutional neural networks are desperately trying to lock onto.
We are a walking math bomb. And finally, the headgear. The face is the primary vector for identity tracking. It is the holy grail of surveillance.
It is.
We utilize custom polycarbonate lenses coated with multiple layers of dielectric hot mirrors. This blocks the massive thermal signature of the eyes and the upper face. and we frame those lenses with aggressive retroreflective microprisms.
For active defense.
If any system attempts an active near-infrared scan to map the topography of our skull, those prisms catch the laser and fire it directly back into the sensor, momentarily blinding the camera and destroying the depth calculation.
It is a robust, layered system. But there is a crucial final step in FMEA. You cannot just buy this gear, put it on, and assume you are a ghost. You must verify.
Trust, but verify.
The zero-mistake mindset means testing everything yourself.
And I am directly challenging you, the listener, to do exactly this. Do not trust marketing copy. Test your own loadout. Build a cheap DIY IR test rig this weekend.
It's surprisingly easy to do.
It is incredibly easy. Go find an old, cheap USB webcam in a drawer. Open it up with a small screwdriver. Right behind the lens, you will find a tiny, usually slightly pinkish square of glass resting over the silicon sensor.
The IR cut filter.
That is the IR cut filter. Its only job is to block near-infrared light so the camera's colors look natural to humans. Take a pin, pop that tiny piece of glass out, and put the camera back together.
And just like that, you have an IR camera.
Suddenly, that $10 webcam can see near-infrared light brilliantly. Put on your expensive, supposedly blackout privacy sunglasses, turn off the lights, point a TV remote at your face to act as an IR flashlight, and look at yourself through that modified webcam.
People are always surprised by this.
You will be absolutely shocked to see how completely transparent those expensive plastic lenses actually are to IR. Your eyes will be totally visible.
That level of rigorous paranoid testing is mandatory because the surveillance grid does not sleep, it does not get tired, it does not get distracted by a text message, and it does not blink.
It is relentless.
Your engineering must be entirely passive and absolutely perfect. You have to stop treating surveillance as a distant political issue and start treating it as a mechanical, physical failure mode in your personal operating system.
So what does this all mean for the future? We've covered the physics, the optics, the metamaterials, the AI exploits. But the grid is evolving. It is getting smaller, faster, or more pervasive.
I want to leave the listeners with a thought that stretches beyond the immediate science we've discussed today, as the world relentlessly pushes toward the concept of smart dust.
Smart dust. That sounds terrifying.
It's the idea of millions of microscopic ambient sensors scattered seamlessly into the environment, painting our cities, embedded in our paint, monitoring temperature, light, movement, and chemical signatures constantly.
So not just cameras, but a literal dust of sensors.
Yes. The arms race between mass surveillance and personal privacy will fundamentally shift. It will no longer be fought in courtrooms with slow-moving legislation or on remote servers relying on digital encryption alone.
Where will it be fought?
It is going to be fought in the physical world. It will be fought through the localized manipulation of the fundamental properties of light, heat, and acoustics on a microscopic nanometer scale.
We have to engineer our own reality.
Engineering your local physical laws, learning how to manipulate the very photons that bounce off your shoulders before they reach a sensor will be the only true sanctuary left.
To subdue the problem without a fight that is the acme of skill,